All right, so why they have this on our first PowerPoint is this is perpetual motion, right? How does the water climb up here and fall here and keep doing that over and over? It cannot happen. So there's no such thing as a perpetual motion machine. Anytime you put energy in, you don't get every bit of that energy out. There's always some energy loss in the form of heat. It's probably the most common form. We can get specific on that heat. Could be friction, can be just heat or resistance. And if you're thinking about becoming an electrical engineer, that's where the money is. The money is, how do you get electricity from the power plant to a consumer's home without losing it in the form of heat? And the better method you can come up with that, the more money the company makes. And there is big research in this. This is the whole thing what drives superconductivity. In superconductivity, we don't get that loss of heat, or we still get some, but we get much less than we get in nitrogen, much less. I mean, 10, 20 more percent of the energy that's pumped out is lost as heat. So if we can reduce that, there's lots of money to be made. The only problem with superconductors right now is generally you have to have something about like liquid nitrogen. You have to have it cooled down to something on the order of liquid nitrogen. Well, we can't afford to put every power line out here with a case on it with liquid nitrogen circulating. So we can't do that. So we just we live with the heat loss right now. But that's where the big money is. You can reduce the heat loss. All right. So first law of thermodynamics. We talked about this in chapter 6. Energy cannot be created or destroyed. Total energy of the universe cannot change. And so that was chapter 6. All right, and this is just a review here. This is just to get us, they have a little review in chapter 17 because they assume you haven't seen this since like maybe Chemistry 170. So we spent our time talking about delta E equals P plus work. We talked about delta E equals delta H plus P delta D. Again, this is what we like when we're talking about a constant volume calorimeter. This becomes the change in volume to 0, and the heat then is specifically related to internal energy. If we're working under constant pressure conditions, then we're solving for delta H. So that was the talk the last time. Delta H is Q at constant pressure. And that's what we work in chemistry because most of the time we're working with an open beaker. All right, so here we're showing major losses in heat. And it's because of these losses in heat, the reaction is not reversible. So here we burn fossil fuels coal. That makes energy. We lose some of the heat here. It's a heat tax. Some of the energy that was contained in the coal is lost as heat, and we're not going to get that back. We use that heat to make steam. The steam runs the turbine here, it generates electricity. We lose some heat here. We transfer the electricity over to the power lines. We definitely lose a lot of heat here. And then that heat goes into your home, and then we energize a heater, and then we get heat in the house here. So every one of these movements has a heat loss. In fact, if you're thinking about being a mechanical engineer, you look at this stuff. You want to make the most efficient automobile engine as possible. You want to eliminate as many of these steps as possible, and you want to reduce the amount of heat that's going to be lost by the engine. And the friction. So you start seeing these newer, I just saw a newer engine, it's like a 2-stroke engine that it was just had like a one, well, it's really kind of like the disc engine. Is that the one? Now that's a rotary engine.
No, not the rotary. I think I know.
What'd you call it?
Disc.
I think it's, yeah, and it's a lot more efficient, yeah. Which then you have the rotary engine like you have in the model, and where you don't have the pistons, you have a piece that rotates and creates these pockets of where combustion occurs. That's a more efficient engine than your piston engine. Yeah.
How do you consider it a heat tax whenever you burn fossil fuel trying to get heat out, and you get actually a heat tax? Where is there a heat tax?
Well, the tax is you don't get 100% of this heat to change that over to steam. Not 100% of the heat released by the coal is going to go to the steam. Some of it's lost to just the environment, to the surroundings. Some of it's lost, and the way it's lost is, and that's what's coming up, that when you generate heat, you increase the entropy of the surroundings. You can't get that entropy back.
And then at the end, whenever you're energizing the heater,
Yeah.
then you lose heat in the heater, which is also heating the air anyways.
But some of the heat here is lost also in entropy and making the molecules move further apart and to give them the more kinetic energy is the heat, the more kinetic energy of
Yeah,
the
but
air.
there's no real heat tax there because any heat that's put into the surrounding is exactly what you're wanting out of the heater anyways.
But it would be nice to have the heat without the increase in disorder, which is the heat tax. Or how about this? Here's another. That's one. Or another way here. Or another way to think of it. You want to think of it specifically as heat. You think about a heater. It has an element in it, and you're passing the current through it, and it's glowing. That's what's given off to you. Well, as the current runs through that element, there is friction. There's impedance there. We call it friction. It's impedance when we're talking about electricity. That impedance is we're losing some of our energy just for resistance of that electricity flowing through the coil, and it's not really being generated secretly.
But that is what resistance comes out as is heat.
Yeah,
Heat coming, being lost before it gets to the element. Being lost, you put in 10 watts, and you're only getting
8 watts of heat in that. That's right. That you feel that's actually coming out.
Yeah. But I mean, any amount that you're losing is going into the system anyways, right?
But it may be going into the system as disorder, not heat. That's where and that's what we're going to get at here. That most of these heat taxes, what they are, is we're losing some of the energy in the form of disorder, not heat. Because you would agree with what he said, that if you put 10 watts of energy in, you're not getting 10 watts of heat out.
Well, there's 10 watts in some form coming out. Just because it's not where you measure it doesn't.
But it's not all 10 watts of heat. Would you agree with that?
I think that a heater it is. It may be lots of before it gets to the heat element. Yeah.
Yeah, the sound,
But
you
the
lose
sound-
some in sound, which that's
the
an
sound turns
indication.
into heat as it dissipates.
Yeah, but sound is not heat, right?
Sound turns into
Sound can turn into heat, but sound is not heat. So I mean, any of those things like sound, light, these are not heat. Those are different things.
Like, so is light and sound forms of energy?
They are they're forms of energy.
That's the word energy.
Yeah, they're forms of energy. But then we also have the disorder. So you would agree with this, that when you put in 10 watts of heat, that some of that
you get 2 watts of disorder.
Huh?
When you get 2 watts of disorder.
I don't think you get 2 watts of disorder, but you do get
I mean,
some
that's what I'm saying. I mean, how do you count?
Yeah, now, you can do that in physics. You will run this current through stuff, and you'll go, well, I lost this much here, and I lost this much here, and I lost this much here. You will start talking about where you lose all of your energy. And you'll do calculations with that. I mean, we would agree with this, that if you pass this current through the element, that the molecules within the element are moving faster, and you've got more disorder. So some of the energy that you plugged in at that 10 watts is just causing disorder within the element itself.
That's almost like work. That's exactly.
Yeah, it is. That is what it is. I mean, when you pass a current through a distance, that is work. It's a type of work. Yeah.
But that's exactly what a heat element does. Is it catches it basically a high resistance thing that when you pass the electricity through, it makes it vibrate. It makes the air around vibrate with heat. I mean, that's exactly what you're trying to get.
Yeah, that's it from just in the element. So there's still circuitry to overcome. We're still wiring.
But
the work that goes into the rest of the element.
Yeah,
but as the wire heats up, leading to it, then that.
So you believe 100% of that energy that you put in the wire is coming out in the form of heat?
It may not be coming out at the front where you're wanting to, but it's coming out in the form of heat.
Would you agree that some of that is not coming out in the form of heat, it's coming out in the form of light?
Yes. But
You agree that some of that is coming out?
a lot of heat is infrared radiation anyways, which is light anyways.
Yeah, that's true. That's part of it.
So, I mean, it's.
Yeah, I can tell you that it's not 100%. It's not. In fact, that's what you look for when you're looking at. Okay, just look at your light bulbs, for instance. You put in. Here's a classic example. Look at your light bulbs. You got a standard incandescent bulb that's 100 watts. You put 100 watts of heat in. You put 100 watts of electricity in it, and you're only getting out. You might be getting out 100 watts of light. But then we can put in 23 watts in a cold fluorescent bulb, 23 watts, and we get 100 watts of light. So something's going on with that bulb that we can put in 23 watts and get 100 watts of light out.
Basically what I'm saying is that most inefficiency processes put out in the form of heat. But when you're wanting heat in the end, then you're not actually losing heat.
Oh, okay. I would say that not all that's going to be in the form. I'm going to say that not all that's going to be in the form of heat. It isn't. It's some of it's in entropy. Some of it's in disorder.
So you're saying that energy turns into
Energy creates entropy. That doesn't turn into it. It creates entropy. Creates disorder. Yeah. Or the lack of energy can remove entropy. Just like when we remove the heat out of this water, the molecules slow down, so we've lost some entropy there. So that's what this whole chapter is about, is the relationship between energy and entropy. All right, we'll move from there. All right, so let's go on. And so spontaneity. Need to know the term spontaneous. Spontaneity just means a reaction will happen on its own, does not require energy to force it to happen on its own. So spontaneity, like the car rusting, you don't have to go out and hook an electrical current up to it or burn something next to it to cause something to rust. It's going to rust on its own. When you take a scoop of sodium chloride and you dump it into water and stir it, the sodium chloride spontaneously dissolves in the solution. There's another driving force there, entropy. You got table salt, which is in these solid crystalline cubes. You put it in water and it separates into its ions all over the water, which makes the solution. That's more entropy. That's more disorder than it all being packed as a solid in terms of solid sodium chloride. So spontaneity is reactions that happen on their own that do not require an input of energy. Other than you may have to add a little bit of an input just to get over the activation energy. But once the process starts, it continues. A lot of students right here at the end, I want to stress this, spontaneity does not mean that the reaction is fast or slow. That's kinetics. We are talking about thermodynamics in this class. This chapter 17 is not about kinetics, it's about thermodynamics. Thermodynamics is about heat and entropy. Kinetics is about how fast the reaction is going to happen. So when we're talking about this in chapter 17, we're not talking about the speed of the reaction. We're talking about will the reaction happen on its own or not. There is energy within, when bonds break, it always costs energy to break bonds, but then the new interaction between the sodium ion and the cage and the water molecules around it, the hydrolysis, that releases energy.
So there's energy being transferred, but it's all being in the same system.
Yeah, so that's right. Yeah. All right, so here's some examples. Yeah, we just talked about these. Here we increase the potential energy by pulling up on this, and that pulls this up. We let go of this, it's spontaneously going to fall down. So direction of the spontaneous change. Same thing here. It takes energy to make this sodium chloride, and when we put it in water, it spontaneously dissolves. And we can compare the spontaneity by looking at the potential energy changes. Looking at the potential energy changes of the system. All right, so reversibility of process. So we know this car is not going to go back and form the new car. So, I mean, that's something we ought to be thinking about is why, when are reactions reversible and when they're not? When they lose a lot of heat, they tend to be non-spontaneous in the opposite direction. When they lose a lot of heat dramatically, or what we're ultimately going to come up with is when we see a lot of disorder and heat loss, those reactions tend not to be spontaneous in the reverse direction. Reactions that are really slow, though, they are your best ones that tend to be reversible. Ones that slowly change from one thing to another and can go back and forth. It's kind of like this. We can freeze water we can slowly freeze the water to where it's a solid. And so when we heat this temperature up, when we raise the temperature, the reaction goes back the opposite way. So above 0 degrees Celsius, we know that at 1 degree Celsius, water wants to be in the liquid form. 0 degrees, both forms exist, and below 0 degrees, then we have a solid. So if the reactions are fairly slow, they're not like an explosive reaction or something like that. If they don't release heat dramatically at one time, they're generally reversible. Yeah. Jay?
No, I was going to ask for another example outside water.
Yeah. I'm going to focus on water a lot because it's easy to explain. When we start talking about chemical reactions, I'll tell you what gets hard about chemical reactions. Like the sodium chloride one. That one's easy to explain. You guys put in the sodium chloride, you see it dissolve. Everybody's had experience with that. How do you get the sodium chloride to come back together? Yeah, you have to evaporate the water off. You have to go back with an input, right? You have to add energy, evaporate the water off to get back to the solid. So that's another good, but the thing I am cheating here, I'll tell you where I'm cheating. When I talk about water, when I talk about the dissolution of sodium chloride in water, these are not chemical processes. These are physical processes. I'm not really giving you an example of a chemical process. Now this is a chemical process. We see a change in color. The substance changes chemically. So that's a good example of a chemical process. But to talk about these changes, water is a good one to focus on. And it gets the concept across without getting technically into the chemistry of the reaction. All right, so we've already talked about this. Reactants, products. This is what we're talking about, chapter 17, spontaneity. Here, speed, intermediates, things like that. That's what we talked about in chapter 13, kinetics. How fast are reactions? How fast do we get to the reactants to the products? This is kinetics. When we talk about heat changes, and when we talk about spontaneity or entropy, we're talking about thermodynamics. All right, so this is my favorite example right here for spontaneity and heat and so forth. All right, so we have diamond over here on the left. We have graphite on the right. All right, it says graphite's more stable than diamond. Lower in energy. We have same amounts of graphite, diamond and graphite. Graphite is more stable. It's lower in energy than diamond. All right, anybody have an idea why diamond would be have more energy in it than graphite? That's right, more structure. It takes energy to make that structure. To make all the carbons network together like this in perfect order to make a diamond, where graphite does have a structure, but it's only on planes. You've got a structure on this first bottom plane, you've got a structure on the second plane and the third plane, but they're not connected like they are over here. There is attraction, that's what those dashed lines represent, but there is not a true bond between these planes. That's why you write with a graphite pencil. When you push on that pencil tip, these planes of carbon shear off and stick to the paper, and you see the writing. That's why graphite's a good dry lubricant. You can put it in a key, and it'll break off and go into the keyhole, and you can manipulate that around. That gives you some lubrication there. That doesn't happen with diamond. It doesn't shear off. Unless we strike at a face, and we can break off the facet there. But again, that's not always easy to do. We see people, you hear about people messing the facet up on a dynamite chipping. So a lot more energy in here, a lot more order than in graphite. So, diamond's higher in energy, diamond has more disorder. Those are the two driving forces that cause things to go degrade, all right? So, diamond will spontaneously change from diamond to carbon, graphite. It will go from this higher energy, more orderly system to this lower energy, less orderly system. So you're all worried about your diamonds now, but the thing we haven't talked about is how fast does the reaction happen. Very, very, very slowly. But I always like the beer's commercial that diamonds are forever. That is not true. That is not true. Yeah, in your lifetime, yeah, but not forever.
We had no idea about how long that process takes.
No, and I don't know if there's a calculation in your book. There might be on the back of the book. But that's not. No, it's not going to be in this. No, because that's a kinetics problem. That's a kinetics problem. Absolutely. This is what happens when people's houses burn down. They think, oh, I left my jewelry in there. I'm going to go find my diamonds. They're gone. They will burn. Graphite, diamond will burn. It's hot enough. This reaction then becomes more faster rate here, and the diamond will burn.
Did you say diamonds have no disorder?
No, more order. Graphite has more disorder. Yeah, more order, more orderly structure. Yeah, if I do say it wrong, you can correct me, and we'll know after I skip my videos, right? So, yeah. Diamonds have more order. All right. Do what? Yeah, I mean, well, it depends, right? We can make one in the lab fairly quickly. I think it takes about 30 days to make a nice diamond in the lab. Now, if you're talking about on a natural scale, we're talking, what, a million years or whatever, under a lot of pressure and a lot of heat. I mean, that's why diamonds are generally found in these volcano tubes. That's, that's generally where you find diamonds, is where there have been previous volcanoes, and then the heat and the pressure eventually changes carbon into the more orderly diamond. So just remember, a diamond to graphite is, and it's a classic example because you see you're moving from more order to more disorder, and diamond has more stored energy in it than graphite has in it. I don't have my clicker today, so that's what's going on. So we've talked about this already, but again, exothermic reaction, you're moving from reactants of higher energy to products of lower energy. Heat's released, we show that as delta H with the negative sign, where we say heat evolved. And then the other type of reaction is an endothermic reaction. That would be the reverse of this reaction. If this was my reactants and this was my products, then we have to increase the energy in the system, and that would be a delta H with the positive symbol. Again, this is from chapter 6. But here's where the question lies, is that, is heat the only thing we have to look at? Well, we know with this ice system here that ice does not liquid water does not spontaneously go to solid water above 0 degrees Celsius. It doesn't happen. So it's more than just heat coming into play here. We also have to talk about the disorder or the entropy. So here's melting ice. We've talked about this. A decrease in, or an increase in disorder, increase in entropy when we go from the solid to the liquid. Up here, nice orderly fashion. Down here, more random fashion. So more disorder. More disorder in the liquid water.
So could entropy be given as a word?
Let's see, can entropy be counted as work? there's going to be a relationship. We generally think of work as, a pressure times volume type of change in volume. We can relate enthalpy to entropy. That's coming up. So indirectly, it can be related to work. Indirectly, yeah. And we'll see that. We'll see an equation like that later. All right. So from here on out, the two things you want to focus on is delta H of the reaction and the change in entropy of the reaction. So bottom here, delta S, the change in entropy is the difference in the randomness of the from reactants to products. Delta H is in kilojoules per mole. We already know that from chapter 6. We know that delta H is negative for exothermic reactions and delta H is positive for endothermic reactions. So this you should. I'm not going to spend a lot of time on that. We know this from chapter 6. Again, this has a this assumes you haven't had 6 in long. All right. So now we get into entropy. What is it and how do we measure it? Entropy is a thermodynamic function, and Boltzmann is the one who came up with this equation. He said entropy is equal to his constant. Notice the units. This is important, the joules per Kelvin. And W is the number of energetically equivalent ways a system can exist. Now, this is what comes into, Joshua, you were talking about, like how we measure the entropy of the universe. What is the form of entropy? It is about, according to Boltzmann, the way he talks about entropy is, it is about the number of positions that a substance can occupy. An atom can occupy in space. So the more space available, the more entropy. Because there's more space is available to occupy than maybe this is, if this is just a circle, a flat circle, there's only so many places it can be occupied here. Open it up to the whole room, we have a lot more spaces to be occupied. No, entropy is going to be joules per Kelvin. Joules per Kelvin. Because see, what's going to happen is you're going to have S equals joules per Kelvin, right? And then I agree this part's meaningless because when you take the logarithmic function of something, the units generally don't mean much. So.
What is that? S G and J per mole, and it says pretty much meaningless, like you said, and it says J per K.
You want?
S G and J per mole.
Yeah, it's J per mole.
So is it J per mole or J per K?
Yeah, when we put it together, we'll probably, a lot of times it's going to be J per mole K. Yeah. So here's how W is explained, this position of entropy. Tell me which one of these systems here is most probable to occur. That's right, so everybody knows this. Everybody can see that this is more probable than either one of these two up here where everything's over to one side. And we know that because the air that we're breathing in this room, if this was highly probable, either one of these, all of a sudden, in one given time, all the oxygen would be up in that corner of the room and all of us be smothered. All right? Now, is that not to say that it's impossible? No, it's possible. There is, that's the whole thing. It might be, the possibility might be 1 times 10 to the 23rd. Or something high. You can actually, there's some calculations, you can look it up and they'll tell you what the probability in a certain volume and all the oxygen used is 1 million grams. So it's not impossible, but it's highly improbable that it's all going to be to one side of it. All right? So these are not impossible states, but everybody knows this is the most probable state of the 3.
So A, B, and lower entropy.
That's right. A and B have lower entropy because you have more possibilities of where these 4 atoms can be in this volume than if they're all on one side. So, this is called, and your book talks about this, macrostates, microstates. Macrostates is this. What we see here, these are the possibilities where these molecules or atoms can be. Microstates is if we label these 1, 2, 3, 4. Think about how many combinations you can have. You can have 1, 2, 3, 4. You can have 2, 1, 4, 3. And those would be different because the atoms are in different places. Those are called microstates. So Boltzmann, what he does is he really applies statistics to the physical universe And that's how he comes up with entropy. So if you really like entropy, you're going to have to get some physics, or you're going to have to get some statistics under your belt, because it's really most people today deal with entropy in terms of statistical methods. All right. I mean, you've heard probability. That's what we're talking about right here. Which one of these was the most probable? It's the last state. All right. So they talk about macrostates and microstates. Macrostate can be achieved through several different arrangements of the particles. And then here are our microstates. And this is what I was talking about. You can have 1, 2, 3, 4. You can have 2, 3, 1, 4. These are all the possible microstates. And what Boltzmann is saying is that the more probable states, the more possibilities of occupation, the higher the entropy. And we know that those states are more probable. That the state that everything is on one side, that's just not likely to happen. The possibility of that versus the other ones is very small. All right, so we're going to just skip over one.
So what did the K and W represent in that equation as equals to K?
Well, K was his constant. K was Boltzmann's constant, and it deals with the distribution of atoms at a particular temperature. That's really what it is. It's about the particles at a particular, what their behavior is at a particular temperature. And then K was what they defined was the number of states possible, the number of microstates. The W. Yeah. So the more possibilities of occupation, the larger W is going to be. And then K is the relationship between, that constant is a relationship between the energy, joules, and the temperature. And we understand that. If we increase the temperature in our system, what happens to the entropy in the system? It increases. All right? If you increase the entropy in your system, like heating up your pot of water, the molecules are moving more energetically. There's more possibilities of where those locations can be. Same thing here with the water freezing. We know if we heat the water up, it's not going to go to the solid. It's going to go to the liquid. When we take the heat away, then we start moving back the other direction, making the solid. And if you're planning to be an engineer, you're definitely going to have to know more about Boltzmann, and you're going to have some statistics there. Because ultimately, that's what you do. When you build a bridge, somebody's got to do the calculations at some point that says we can hold 240 tons on this bridge, and it should not fail. And it shouldn't fail. And then you generally put in a safety factor of maybe, it used to be 4 times the amount. Now it's about 2, 3, I think. So you put in that. Somebody's got to do a statistical probability of this bridge failing before you sit there and sign off on it. So you got to have some statistics. Somebody does to figure out what the probability of failure is. All right. So how do we measure entropy changes? Well, the easy way to measure it is to just look at the entropy final minus the entropy initial, just like we looked at delta H. So that means you have to know what the entropy of the molecules and atoms are before and after the reaction, and that is possible. What I do want you to get out of this is a positive entropy change means that the disorder has increased. All right? So you need to know this. Because this is what I see on the exam. Students get confused between, we know that delta H negative is exothermic, and we know that means that reaction is likely to happen. If we don't think about anything else, we know that things want to move to more or less energy stored in them. It's just like when you roll a ball down the hill, the potential energy decreases, or if I drop this, the potential energy decreases. It's an exothermic process. But for entropy, you want a delta positive if you want something to happen spontaneously. You want a delta S to be positive. So a positive change in entropy means more disorder. So if you want to make sure a reaction is spontaneous, it doesn't talk about how fast it happens like the diamond, but if you want to ensure that the reaction is going to be spontaneous at any temperature, you want delta H to be negative, you want delta S to be positive. These reactions are spontaneous at any temperature. So what happens when delta H is positive? You have an endothermic process, and delta S is negative. You're moving towards more order. Is this reaction going to be spontaneous or non-spontaneous? Non-spontaneous at any temperature. That means this reaction doesn't happen unless you start changing the mechanism. You either add a lot of energy. It's not to say it never can happen. It's just that you're going to have to alter it some way to get some of this to change, to get something to change here. All right? So, in our example of H2O going to H2O solid, what's delta H for that reaction? Positive or negative? Negative. We're going from here to here. Final minus initial is going to be, well, it's exothermic, but if I say final minus initial here, am I going to get a positive value or negative value? Negative. All right, so we got this. You got to have this part down to understand 17. You got it? This is 6. All right? Now, delta S, positive or negative? Negative. You're going from more disorder, free molecules that can flow over one another in a liquid, to a nice ordered system of water molecules that form some type of space like that, a crystalline solid like that. That's why ice floats. Ice forms these nice little crystalline solids with a void in the middle, and so the density of ice is less than the density of water, so ice floats. It'd be in bad shape if ice didn't float. So that's a strange property of water. Water is a strange stuff. You can spend a lifetime, if you want to do your entire lifetime on water, you still can do that. There's so much we need to know about water. If you really like water and you want to focus on that, you can do it. Because it is, with most solids, when they go from a liquid to a solid, they get more dense. Almost everything, when it goes from a liquid to a solid, becomes more dense. Ice is just the opposite. So, delta H is negative, delta S is negative. When does this reaction become spontaneous? At what temperature? Low temperatures or high temperatures? Low temperatures. It doesn't freeze until you get below 0 degrees Celsius. Or 0 it starts, and then we're at equilibrium at 0 degrees. You can have water at 0 degrees Celsius and ice at 0 degrees Celsius. So low temperatures, this reaction is spontaneous. At high temperatures, it's not. We try to do this reaction at 100 degrees Celsius. No way water is going to go to ice at 100 degrees Celsius. So only at low temperatures is this reaction spontaneous. All right, let's do another one. Draw me an energy diagram of H2O water, liquid, going to H2O gas. Draw me a same type of energy diagram for that. All right, so you should have water here, liquid, and then up here is steam. And there's our activation energy from here up to here. All right, and from here to here is delta H. Is delta H positive or negative? Positive. You had to input energy to get that liquid water to break the attraction, the intermolecular attractions, so that they actually act independently as a gas and steam. All right, so delta H is positive. What about delta S for this reaction? Positive. We're going from an orderly liquid to a less disordered gas, so delta S is also positive. When does that reaction become spontaneous? High temperatures. That's right, high temperatures. Only at high temperatures does this reaction become spontaneous. Now we got to figure out what we know for water. It's 0 degrees for this reaction to be spontaneous. For the freezing of water, it's got to be 100 degrees for the reaction for water going to steam. So we can figure out, we got to be able to figure out what that temperature is. Where does the temperature lie where it becomes spontaneous? What do we call it when it goes from a liquid to a solid? What's the term we use? Freezing. So the freezing point is where that spontaneity occurs. And what's this over here? Boiling or vaporization. Generally we like to say vaporization because boiling is a specific type of vaporization. It's the same kind of principle. Yeah. Okay, so here's a good question because I find most of my students do not get this correctly. When we talk about boiling means that a bubble is forming under the liquid. And what's inside the bubble here? What kind of gas? H2O gas. Now, if I ask my other students, my 140, 120 class, they either think it's hydrogen or oxygen gas. But that's not the case, because if it was, the stove would blow up anytime you boil some water, right? Hydrogen would spill over the top, hit the element, and it would explode. So it is H2O gas, and it's a bubble within the liquid. So you're not only overcoming the change of the water, the forces between the water, liquid, and the steam, you're also overcoming the pressure of the atmosphere above it and the pressure of the water above it, although we don't talk about that one as much. That's why you know, if you want to boil water rapidly, you don't put it in a big stock pot that's this high, because then you got all that mass of water above it. You want to put it in a shallow pan to boil. It boils much faster in a skillet than it does a saucepan because of that mass above it. We know water boils at higher elevations. It doesn't require a high temperature to cause it to boil. So that's what boiling is. Evaporation is that there's water molecules on the surface of the liquid, and the water molecules on the surface and the ones below have movement, kinetic energy. Eventually, they transfer that kinetic energy to a water molecule on the surface, and it gets enough energy to escape. That's what evaporation is. They both require kinetic energy to break the bonds of intermolecular forces. But this one doesn't require as much because it doesn't have to work with this mass above it. So that's why we just generally say vaporization, because that includes both of those.
It doesn't necessarily have to occur at 100 degrees Celsius.
Oh no, that's right. It is spontaneous. I mean, it's 25 at 25 room temperature. After all of these molecules are moving, and they eventually bump into this enough to get this one to break off.
What are the signs for your age?
Oh, okay. On both of these have a delta H of positive. You have to put energy into that molecule to get it enough kinetic energy to escape, and both of them are going to have delta S's that are positive. Yeah. All right.
In the case of evaporation,
yeah.
Like what happens when you dense, like there's only like a few individual molecules of water and they can't like bump into each other as much?
Well, then you start interacting with the container itself, right?
Okay.
I mean, the containers vibrate like this. Whatever container you have, it's vibrating, and it eventually transfers. So it eventually will evaporate to nothingness. Yeah. All right. I mean, I think a lot of people don't get that this table is vibrating right here. Everything in here is at least, every solid in here is vibrating. It is moving. And that's actually what the third law of thermodynamics is the third law says the only thing that has zero entropy, zero disorder, no disorder whatsoever is a pure crystalline solid, no flaws in it, pure crystalline solid, 0 Kelvin, which is a theoretical point. It means the electrons aren't moving in that substance either. So, there's the advantage of entropy over enthalpy. Enthalpy, we had to arbitrarily come up with our 0 point. So what we said was, any element in its standard state at room temperature, 1 atmosphere pressure, has a delta H equal to 0. We defined that. We made that. But the definition of entropy is, it's very specific. It's a pure crystalline solid. It means it's very ordered. And it has it's 0 Kelvin, so the electrons, because even if an electron is spinning around the atom, that's disorder. That's movement. That's places where the electron can occupy. So the third law of thermodynamics is that a pure crystalline solid, 0 Kelvin, is 0 entropy. All right? So we've seen this increase in entropy in a month. increases in entropy. All right, you need to know this equation here at the bottom. This equation is looks like the same form of the equation that you used in chapter 6 to calculate delta H. Delta H for the reaction, delta S of the system is equal to delta S of the reaction. Okay, so delta S of the system is equal to delta S of the reaction. The reaction is what we're looking at. But remember, I don't know why they did this, but I will stress this point. What is the system? The system is always what you're interested in investigating, which in this case is the reaction. So don't get crazy about what the system is. The system is what you're investigating. Everything else is the surroundings. And the system and the surroundings together is equal to the delta S of the universe. All right. So you've seen this before. In the last chapter 6, we have the summation, the number of moles of delta H of standard enthalpies of formation of the products minus the reactants. Well, we can do the same thing for entropy. The summation of the number of moles of your products for each product, it's S, it's entropy. We don't have to have a delta S here because we have a definite defined point of what zero entropy is. So we just need to find what the entropy of that product is, which is in a table in the back of your book, minus the summation, number of moles of the standard entropies of your reactants. So this is called the direct method. If they ask you to determine the entropy change of a reaction, you're going to find the entropies of your products and your reactants, multiply each one by its number of moles in your balanced chemical equation, and you're going to find the change in entropy of the reaction. Just more of the same here. Okay, so why did I put this slide in here? The only thing the reason why I put this slide in here is just to say, it all comes back to Boltzmann's equation. There's a lot more freedom of motion in these gases than there are in solid. All a solid can do is vibrate back and forth, translational movement. Here we got rotational, or here we have vibrational. Translational just means movement out and this, movement, right? So here, when we have them, they're free from one another. We have rotational movements. We can have scissoring. There's all different types of movements you can have when you're an individual molecule versus a solid. All right, we've done this. Pretty much talked about the entropy changes for water. Solid, not much entropy. Liquids more. Gases the most. All right, so I want you to be able, you're definitely going to see this on the quiz and exam. I want you to be able, without looking at any numerical value, this is conceptual, I want you to be able to look at these things and tell me whether you see a positive entropy change or a negative entropy change. All right, hot beaker burning your fingers. Positive entropy change or negative entropy change? I'm looking at my fingers because that's what I'm interested in, right? It's positive. The heat transfers from the beaker to your fingers, and if it's bad enough, it actually starts breaking down the structure, right, of your finger. You get a nice blister on there, or at least turns red, which tells you there's swelling there. So there's movement, there's more entropy in that burn than there was before you burned your finger. So that's a positive entropy change. Yeah.
So if this is an endothermic reaction, it's going to have a positive entropy change.
If it's an endothermic reaction, no, we saw here you could have an endothermic reaction with a positive entropy change or a negative entropy change. Yeah, you can have either one. The entropy is separate from. Yeah. Well, it's because the ones that are visual that you guys know, it's going to be the ones that are mostly spontaneous, right? So that's why I agree. I've been emphasized. That's why we like the water one, because you guys know water backwards and forwards. So that's why I chose that example. And it depends on where you're starting, whether it's positive or negative. All right, water vapor condensing. Negative. You're going from this random molecules and they're starting to stick together as a liquid, so that's negative. Separation of oil and vinegar. All right. Does anybody think it's positive? It is negative. Positive would be more disorder. The oil and vinegar, when they separate and they're in their own layers, there's less disorder than all them little oil droplets suspended in the liquid. So this would be, the separation here would be negative. All right? Dissolving sugar in tea. Positive. Lead 2 oxide dissolving it, or changing to lead oxide and oxygen. Positive. Ammonia breaking down into 2 gases. It's positive. You went from 2 moles of gas on the product reactant side to how many moles of gas on the product side? 4. 4. So you're going from 2 to 4. In fact, that's why ammonia is an explosive, right? You use ammonia as explosive because you're going from 2 moles of gas to 4 moles of gas. And so that expansion of gas very quickly is going to cause an explosion. What about the last one? It's negative. You got these nice ions float. They're in the solution. All of a sudden they start sticking together and precipitating out. When they stick together, you've lost some entropy there. All right, so here's my finger. It's nice structure. And then when I touch this hot beaker, that heat's going to go from the beaker into my finger. And all of a sudden, that heat's going to cause these molecules to move really much more readily in my finger. Right? That's what burn is. You start to break the chemical bonds in your finger. And you get new substances like whatever, the plasma or whatever to burn it and all that. So I want to get to delta H before we leave here. And we will. I don't have much. I just want to get. That's what the focus of the next lecture is going to be on. I can't stress enough that you do need to read this over the weekend. Since we're only having 2 lectures on it before the exam, you're going to have to read some here on your own and come in here if you don't understand something on Monday. We'll focus on it. But the main focus on Monday will be delta H. There's about 3 or 4 equations with delta G. And those 3 or 4 equations is what I'm going to focus on Monday. All right, second law of thermodynamics. We've already talked about this. We just said that most people believe the change in energy of the universe is increasing. It is greater than 0. And if you believe that, then you believe the universe eventually gets really cold. Or you think, if you don't believe that, you say delta S of the universe is equal to 0, and we're right now in the full expansion of the universe. At some point, we've got to do equilibrium, we've got to do a contraction, and if you believe that, you believe in the big crunch. So that's what this slide is about here. And like I said, most people believe the universe is going to expand. We've already talked about that one. I'm skipping over that one. We talked about what's spontaneous and what non-spontaneous is. I do want you to focus on this. I thought this was the most interesting. So when you're reading the book, we're not going to get to delta G. This is the last thing I want to talk about. When you're talking about a process, I want you to think about the relationship of delta S of the universe, delta S of the system, delta S of the surroundings. And this is what I want to leave you with, because I want you to think about this and think about what's going on. This is what people have the hardest time about entropy. Whenever you're taking biology, and you go, I don't believe this stuff about the entropy of the universe increase. I don't believe it. And the example they always want to give me for that is plants grow. So this is what people will argue. They will say, all the minerals and all the things that grow that plant in the soil, they're dispersed throughout the soil, and so you have entropy there. All those particles that make that plant are all out here, and all of a sudden they grow and make the plant. And the plant has more order in it than the soil does. Because once you say, this is my stem and this is my flower, now you decrease the entropy. This is less disordered than all this stuff being back in the ground, dispersed throughout. So, there is an argument, though, that this ends up creating more disorder in the universe versus it being in the ground. So that's what I want you to focus on. Think about that before you come to class on Monday. All right? So tell me how plants create overall more disorder in the universe versus not growing the plant. All right? We will talk about delta G on Monday. And if this has been recorded, and I hope it has, I will place this on